Right now, somewhere beneath the ocean floor, cars are moving. Millions of tons of seawater press down from above. The ground beneath is a shifting mixture of sand, silt, and unstable sediment. And the only thing standing between those drivers and a catastrophic flood is a wall of concrete and steel assembled with near microscopic precision, in complete darkness, at the bottom of the sea. Underwater tunnels should not be possible. The engineering required to build them defies almost every instinct about what construction can achieve. Yet there are hundreds of them operating right now across the world. This is exactly how they are built. Before a single shovel hits the ground, every underwater tunnel starts not with construction, but with months, sometimes years, of investigation into what lies beneath the water. Engineers conduct comprehensive seabed surveys. They map underwater topography, collect soil samples from the seafloor, and analyze rock layer by layer to understand what the ground is actually made of. Is it soft clay that compresses under pressure? Dense rock that resists cutting? Underground water channels that could flood a construction zone in minutes? Every potential hazard has to be identified before work begins. A mistake discovered 30 meters below the ocean floor costs exponentially more to fix than one caught on a blueprint. Environmental teams work alongside engineers throughout this phase. Marine ecosystems are assessed, species are cataloged, and construction plans are adjusted to minimize disruption. Noise mitigation measures are built into the timeline. In some projects, artificial reef structures are installed nearby to compensate for any habitat disturbed during the build. Only once all of that groundwork is complete does actual construction begin. And when it does, engineers have 4 main methods to choose from each one, designed for a different type of terrain, depth, and geological challenge. Method 1, the immersed tube. The immersed tube method is one of the most widely used techniques in underwater tunnel construction. And when you understand how it works, it is also one of the most audacious. Instead of building underground, engineers build the tunnel on land first. Massive reinforced concrete segments are prefabricated in controlled factory conditions. Each standard element measures approximately 217 meters in length and weighs over 73,000 tons. Every single one is manufactured to exact tolerances because these pieces have to fit together perfectly once they are on the ocean floor. Once complete, the segments are floated out to sea on pontoons and carefully lowered into pre-dredged trenches cut into the seabed. Specialized cranes position each segment with extraordinary precision. Then, the sections are connected sequentially, rubber gaskets sealing the joints between them to prevent any water infiltration. Layers of sand and gravel are placed above and around the completed tunnel to hold it in place against the buoyancy of the surrounding water. Only after every connection is locked and verified are the temporary end bulkheads removed, transforming a row of individual concrete boxes into one seamless, watertight tunnel beneath the ocean floor. The Hong Kong-Zhuhai-Macau Bridge uses immersed tube sections for its undersea tunnel segment. Those sections were lowered to the seabed with gaps between them smaller than the width of a human finger. The limitation of this method is terrain. It requires a stable, relatively flat seabed and calm currents. In areas with strong turbulence or complex underwater geology, a completely different approach is needed. Method 2, the tunnel boring machine. When the immersed tube method is not practical, engineers bring in what is arguably the most impressive piece of construction equipment ever built: the tunnel boring machine, or TBM. A TBM is not a drill. It is an entire underground factory on wheels. It excavates soil, removes debris, and installs reinforced concrete tunnel lining simultaneously in one continuous automated process without ever stopping. At the front sits a massive cutter head, typically around 12 meters in diameter and weighing over 200 tons. It is equipped with 140 high-strength steel cutting discs rotating at approximately 2.7 revolutions per minute, exerting pressure up to 400 bar, enough force to crush compact rock and dense soil. The excavated material is immediately pulled into a chamber behind the cutter head, where foam and water are injected to maintain earth pressure balance. This is critical. In soft, water-saturated ground, the pressure inside the chamber has to precisely match the pressure of the surrounding earth. Too little, and the tunnel face collapses inward. Too much, and the ground above starts to fracture. The slurry travels on a conveyor belt back to the surface and is removed by truck. Meanwhile, at the rear of the machine, precast concrete segments are automatically installed ring by ring. Once a full ring is complete, a grout injection system fills the gap between the lining and the surrounding soil, locking the structure permanently in place. Then, hydraulic cylinders push the entire machine forward, and the cycle begins again. Each cycle takes roughly 90 minutes. In a full day of continuous operation, a TBM produces approximately 20 meters of finished tunnel. Hundreds of engineers monitor the operation around the clock from a control room, watching pressure readings, temperature data, power systems, and live camera feeds from inside the machine. China's Jinghua TBM drilled over 7 kilometers of tunnel directly beneath central Beijing, 150 meters below streets, carrying millions of people without a single sinkhole, crack, or disruption to the city above. Method 3: drill and blast in areas with hard geological formations where TBMs cannot operate effectively. Engineers use a method that sounds almost primitive, but remains one of the most effective tools in underground construction. It works in cycles. Dozens of blast holes are drilled into the tunnel face, according to precise technical blueprints. Explosives are inserted into each hole, fitted with electric detonators timed to fire in carefully controlled sequences, each one at a slightly different moment, controlling rock fragmentation and minimizing shockwave vibration to the surface above. Before any detonation, every explosive is scanned, tested, and certified. Each blast breaks approximately 1.5 meters of rock. Between 9 and 18 blasts are conducted daily depending on the geology. The method offers faster progress in hard rock and significantly lower equipment costs than a TBM, but the intense vibrations it creates can crack nearby structures and cause water infiltration, which is why it is strictly reserved for mountain tunnels and dry ground. Never underwater. Method 4: traditional excavation. When every other method fails, when geology is too unpredictable, water pressure too extreme, or the ground too unstable for any machine engineers, fall back on traditional excavation. The process begins by sinking a vertical shaft from the surface down to tunnel level. This shaft becomes the lifeline of the entire operation, the route through which workers, machinery, materials, and excavated debris all travel in and out of the site. Hydraulic cutting tools slice through sediment layer by layer. It is slower, but it gives engineers direct, precise control over every centimeter of excavation in the most challenging conditions on Earth. After each phase, the newly exposed section is immediately reinforced shotcrete applied to the walls, steel arches installed, mesh reinforcements locked into place. Teams monitor air pressure and dewatering systems around the clock. Any imbalance between internal and external pressure can allow seawater to infiltrate, and in a traditional excavation environment, that can flood entire sections in minutes. After the tunnel opens, construction finishing is only the beginning. Before any tunnel opens to traffic, engineers run a full battery of tests: waterproofing integrity, pressure resistance, fire safety, ventilation performance, and structural stability under load. Modern underwater tunnels are typically built with 2 levels, doubling traffic capacity without expanding the physical footprint. Emergency exits are positioned every 200 meters. Hundreds of sensors installed along every tunnel continuously monitor pressure, temperature, humidity, and vibration, transmitting real-time data to a central control room where engineers can detect the earliest signs of structural fatigue before they become failures. With that level of maintenance, a modern underwater tunnel operates safely for decades, enduring the constant pressure, moisture, and movement of the ocean above it. Every meter of these structures represents a decision made by human beings to refuse the limit that water once placed on where we could go. If this broke down something you have always wondered about, hit like and subscribe. More of this coming soon.